I'm Rowan.
I'm Jerome.
I'm Clinton.
I'm Jason.
Did you know that you can calculate the speed of sound at 0 degrees Celsius using your phone, some crickets, and a modified cooler? It's really easy. Let us tell you all about it.
First, let's set up the environment. Create a modified cooler using thermoelectric Peltier modules. When a current passes through these modules, heat transfers from one side of the module to the other. This is known as the Peltier effect. There will be a cool side and a hot side, so use a GPU heatsink with fans to cool the hot side. The colder the hot side gets, the cooler the cold side gets as well. Use fans to blow the hot air away from the cooler and cold air into the cooler. Next, fill up a quarter of the cooler with snow. Then, line the bottom of the cooler with newspaper. Allow the thermoelectric coolers to lower the temperature of the cooler. How do we know if it's 0 degrees? Well, we can find out using crickets and a glass of water. Adjust the cooling of the Peltier modules through positioning a fan above the Peltier module. Place a cup of water inside the cooler. Wait 20 minutes. If you see any droplets of ice, stop. Else, keep moving the fan closer and closer to the Peltier module until you start seeing droplets of ice. This is the point where the temperature is around 0. We can also use crickets to determine the temperature. Dolbear's law shows a relationship between the number of chirps and the air temperature. According to Dolbear's law, the theoretical cricket would chirp negative 30 times every 60 seconds. In practice, this is impossible, and crickets enter a state of diapause when temperatures get too low. Hence, while the idea is very interesting, this is not possible in practice.
Once the temperature has been calculated to be around 0 degrees, place 2 phones facing each other on opposite ends of the cooler. Using a non-ruled string, mark the distance between the 2 phones. This is your reference string. Create a simple swing for your phone to prevent spinning and use a piece of cardboard measuring about 9 by 12 centimeters. With 2 strings running through the holes of the swing, tie a knot about 4 fingers above the swing. Using the non-ruled string from earlier as a reference, tie the string to a protruding bar at the length where the distance between the center of the swing and the top of the string is equal to the length of the reference string from earlier. Perfect. Open Firefox and press the pendulum experiment. Attach your phone to the swing and press play. Release the phone from a height about a quarter of the way from the bottom of the swing. Allow the app to normalize to a single number. Record this number as the length of the string and consequently the difference between the 2 phones. Put someone on one end of the cooler and put someone else on the other side of the cooler. Go to acoustic timer. Adjust the threshold so that the background noise from the fans doesn't trigger the timer. Go to sequence so that you can take 5 trials. Have one person clap on one side. This starts the first timer immediately, and the timer on the other side starts after delay. Now, have the other person clap. This stops the second timer immediately and the first timer after a delay. Repeat this 5 times. Now we have all the data we need to find the speed of sound at 0 degrees Celsius.
Sound is a wave, so it doesn't accelerate, which means we can calculate the speed of sound using the relationship between speed, time, and distance. V equals d over t. We measure the distance of the opposite ends of the cooler by using the string measured by the pendulum theory. When a person claps from the one end, the first phone on the same end will start first, and the second phone on the other end will start in a delay due to the time that takes for the sound to reach. Now the second clap from the other end of the box will stop the timer. The second phone stops immediately, and the first phone where the timer started first will stop in a delay. That will be the double of the delay for the first timer, and that delay is what makes us find the speed of the sound. When the first clap occurs, the equation can be set up as V equals d over change in t. However, we need the timer to be stopped to calculate. The second clap occurs from the other end, so that both phones don't get the same result of time value. Then the final equation will be V equals 2d over change in t. Because the Firefox app could only show a third digit of the decimal value, the value couldn't be exact. So we made many trials and we used the mean of all values found, add up all the results, and then we divided it by 5, which is the number of tries. Then the final result was shown as 322 meters per second.
Light and speed travel at different speeds. Since light travels so fast, we can use the optical stopwatch, which uses the light sensor on your phone, and the acoustic stopwatch, which uses the microphone to calculate the speed of sound.
Using a speaker and a small LED, create a mechanism that creates both light and sound at the same time. Position two phones at one end of the cooler, one with the acoustic stopwatch selected and the other with the optical stopwatch. Position the mechanism at the other end of the cooler. Put both stopwatches in sequence mode, turn on the mechanism 5 times. Record the data each time.
At 0 degrees Celsius, sound travels at around 330 meters per second, while light travels at around 300 million meters per second. Since the speed of light is so great, Firefox will not be able to notice a delay with light, while it will notice a slight delay with sound. Hence, the difference between the optical stopwatch and the acoustic stopwatch is going to equal the time it took for sound to travel twice across the cooler.
Due to mishaps that have occurred during the experiment, we were unable to extract reliable data from the optical stopwatch. Therefore, we couldn't really get useful data from the experiment itself in order to calculate the speed of sound at 0 degrees Celsius. We are going to find the fundamental and second harmonic standing waves in a closed tube of a certain frequency. I have my pipe here that's submerged in water in a tall cylinder beaker. And using this speaker here that's going to be emitting a frequency of 600 Hertz, I'm going to hover it over the pipe and I'm going to slowly raise it until it starts resonating. That's when I know that this length is the fundamental standing wave. See, it's 0 degrees because the roof frosted over. Okay, I have my beaker and my pipe, and I have my speaker here that's going to be emitting a frequency of 600 Hertz using the tone generator function of Firefox. And now I'm going to hover this over until I lift it. I get a strong resonance like that, which seems to be right there. And then I'm going to mark it with my finger right where it meets the water, just like that. And now I'm going to dry it off. I dry it off with my jacket. Still got it right there, as you can see with my finger. And now with a big red Sharpie, I'm going to mark that area. Next, I made a ruler with lines with a 0.5 centimeter distance in between, which I derived from the inclination tool on Firefox. And with some trigonometry, I found the angle, found it on Firefox, angled like this, and then I used a toothpick to find the actual length from my phone to the tabletop, which is 0.5 centimeters, and I made this my concrete measurement instrument. In order to measure the speed of sound at 0 degrees Celsius, we first have to find the wavelengths of both the fundamental and second harmonic standing waves. For the fundamental, I used the formula 4 times length. For the second harmonic, I used the formula 4 times length divided by 3, where 3 represents the number of notes, which is the number of areas in a standing wave in a closed tube where air molecules do not really oscillate. Then, I have to find the speed of sound using the formula velocity equals frequency times lambda, or wavelength. When I found the value for the speed of sound for both the different standing waves, I then added them together, divided it by 2 to get the average mean. To get the uncertainty, I used the formula range divided by 2, which equaled 0.3 meters per second for me. So when I put the two together, I got 319.5 plus minus 0.3 meters per second.